Hey, welcome back. Here we are. We're looking at the Raleigh criteria, and I set up a little question here related to the moon landings. There are a set of people who actually think we didn't land on the moon, which is incorrect. We did land on the moon. But in any case, one of the arguments that can be used is like, well, why don't we just point our telescopes at the moon and then we could, see the footprints or something like that. So this question using the Raleigh criteria will debunk that idea, and let's take a look at what's going on. If you haven't already watched the video on the Raleigh criteria, which is the previous DDD before this one, then you should do that first. Make sure you kind of understand what's going on already before you do an example with it. We have two footprints. We're going to assume stars are often what we talk about. This is going to be instead a footprint and another footprint. And then this distance here is obviously not to scale because this is the distance to the moon. This is going to be 384,000 kilometers. And then this is only 1 meter. So this angle here, I stretched out the image, but it's still not stretched enough. This angle is going to be tiny. And this is the actual angle, observation angle between those two objects as viewed from Earth. And that angle is either bigger or smaller than the Raleigh criteria angle. If the Raleigh criteria angle right here, right, gives us a certain angle that if we're smaller than that, if the actual angle is smaller than that, then we won't be able to tell there's two objects. These two diffraction patterns that we get, right, the single slit diffraction patterns will be too much on top of each other and we won't be able to distinguish them. If instead the actual angle is much bigger than the Raleigh criteria angle, then we will be able to see them as two separate objects when it's on this photographic plate. This is probably like a CCD imaging, like in a digital camera or something like that, where you've got certain pixels that are going to be recording these images. And if the actual angle is too small with a given lens, then the light's going to be landing on the same pixel and you won't be able to tell them apart. They got to land far enough away from each other so that the camera can make up that difference. The doorbell just rang. This is my fourth take on this one, so I'm not going to stop. We're going to keep going. So anyway, we're going to get the actual angle first, and then we're going to also get the Raleigh criteria angle, and then we're going to compare them to each other if I'm not interrupted too badly. We'll see what happens. Okay, the actual angle is really easy to get because you know this is 1 meter, and you know that this distance here is 384 million meters. Whoa, that is a really narrow triangle. If this is only 1 meter, this is 384 million meters. This is not drawn to scale. This theta is going to be tiny. And in order to figure out that angle, you could do an arctangent and then turn the degrees into radians because everything's in radians here. But you know what? Radians is related to this arc length right here. This arc length theta, right, in radians. And if this is the unit circle, then tan theta, right, and the radians is going to be off by just that difference in length between going this way and going this way, which is almost the same length. So for small angles, you don't even need to do an arctangent. You can just take this distance divided by this distance and be done. Check it in your calculator right now. Go through this whole math and figure out what that angle is in radians using whatever, you guys are great at doing arctangents and stuff like that. Turn the degrees into radians and get the answer. And then just notice that you get the same thing if you take 1 divided by 384 million, okay? Because the angle in radians is just the opposite over the adjacent period if the angle is really small and you're in radians. Okay, so that's easy to get the actual angle, and I'll scroll up to see that actual angle. So the actual angle, we're going to take x divided by d, and we get a very small angle in radians. Now it's small, but the question is it smaller or bigger than the Raleigh criteria angle? That's what really matters. Oh, I still have this on. Get rid of this. So the Raleigh criteria angle, you got this adjustment because it's a telescope, because it's a circle. And when you have a circle, you have to do this adjustment on the diameter and not use just theta equals lambda over b, but instead use this equation. So we will. For lambda, we got to say, well, what wavelength are we using? This is visible light. So you'll use green, somewhere around 550 nanometers for lambda. And then B is the size of the telescope, the diameter of the telescope. So we're going to get a really small number here, right? The question is, how small will it be? So let's take a look. And it looks like the Rayleigh criteria angle, 1.22 times lambda divided by b. And right here using the nanometers, 10 to the negative ninth for the nanometers to be in meters. These units have to be the same so that when you divide them, you get radians. Just like up here, units had to be the same. And when we divide this, we get 2.8 times 10 to the negative seventh, which is a small number, but it's like 100 times bigger than the actual angle. So the actual angle is way too small for this particular Rayleigh criteria. So I put no way Jose, you cannot see the footprints at all because the actual angle between the footprints here is much smaller than what the telescope can resolve, right? Because the telescope is limited in its ability to resolve. It can only resolve the Hubble like something like this amount of degrees, 0.0000016 degrees roughly is what the Hubble telescope can resolve. So that's just not enough to make out the footprints. So what we discovered is that the Rayleigh criteria angle here, right, is such that the actual angle puts these bumps on top of each other in a way that you can't tell what's going on. They all just look like one image. Okay, so that's a quick example of how we use the Rayleigh criteria angle to be able to figure out whether or not something is discernible. If you want to do this in person, I'm going to do a little mini lab with you that you can do at home. A real short little exercise to check out how good your eyes are, like an eye test kind of thing. But the other thing you can do is look at the stars outside. The pollution is really down with what's going on. And if you haven't been outside at nighttime to look at the stars, you can see some beautiful constellations right now. Venus is just like, Venus is huge and bright. So if you can get out on your balcony and look at the stars and see what can you make out if you have two stars really close to each other, you're able to resolve them with your eye. There's actually binary stars in the Big Dipper and in Orion such that they can be used as eye tests and just like how good your eyes are based on how can you resolve that there's actually two stars there instead of just one star there. Anyway, go outside and just look at the pretty stars. It's nice out with the pollution being less, especially on the weekends. So good luck. I hope Rayleigh criteria is going for you and you're understanding these ideas. They're pretty cool and pretty important for optics and telescopes and that kind of thing. So see you again soon.